Hi, this is Mr. McGovern, and welcome to the second video in the circular motion series, where we're going to talk about forces in circular motion. So we'll go back to our idea of the whistle tied on the string, spun on this horizontal table. So we're looking down on the whistle. This is a bird's eye view. And to make it really easy, it's a really smooth, frictionless table. So let's now look at the same whistle spinning around the table but from the side, and we're only going to think about the vertical forces, just the up and down forces, just to get them out of the way. First thing we do when we do our force diagrams, we identify the system. This makes it easier to see what's interacting with the whistle. So it's pretty obvious now that I've got my gravity acting on the whistle by the earth. That's the one I normally always draw. And then what else is acting on the whistle? The table is as well, and that's a normal force. So normal on the whistle by the table, and those two are going to be balanced out with each other. So there's my vertical forces. Haven't even worried about the horizontal ones for now, just my vertical. So let's go back to thinking of for the horizontal forces, the bird's eye view. We identify the system and we say what's interacting, what's from outside that system is coming inside the system and touching the whistle. That's what interacting means. And there's only one thing that I can see doing that, right? And that's the string. So there's a tension force on that whistle by the string. Now I've got that pointing inwards. Why? First of all, it's the only thing I've got there. So as I said before, nothing else is interacting with it. And the other rule we had was no touchy, no forcey. The string is touching the whistle, so that's why it's allowed to have that force there. I've told, certainly my class as well, many times that strings can only pull. If you get a string and you tie it to something, you can't push that thing. You can only use the string to pull it. So strings only apply a pulling force, and therefore the force on that whistle by the string must be pulled towards the inside of the circle, not pushed outwards. So there's my forces, my three forces that contribute to circular motion for this whistle. The total force in circular motion always points towards the center. Okay, that's a key rule you need to be able to remember. And in circular motion, we give the total force a special name. It's called the centripetal force. It looks like it's read centripetal, but it's said centripetal. It's not its own force, it's a special name we give to the total force. So what have we got so far in the first two videos? We've got velocity in the circular motion always points tangent at the point. The velocity is changing because the direction changes as it goes around a circle, therefore the object's accelerating. The total force we just worked out points towards the center. This is called the centripetal force. I'll often label it just as the total force. And we also know that total force equals mass times acceleration, Newton's second law. Therefore, if the total force points towards the center, the acceleration also has to point towards the center. So we've got three different vectors there. Because they're different types of vectors, you make sure you label them so you know what they are. But you have to know for any object going around a circle, velocity is tangent, and total force and acceleration always point towards the center of the circle.